So guys, today we'll be talking about valence band, conduction band, semiconductors, and Fermi level gap and band gap as well. So let's start a discussion with valence band. So before we dive into definition, let us see what is valence band. So this is nucleus and there are shells around the nucleus, and this is what we call as atom. And electrons revolve in these shells around the nucleus. The outermost shell from the nucleus of an atom is known as valence shell, and the electrons which revolve in this space are known as valence electrons. So electrons revolve in this way. So, and let's take one more atom in the same way. Electrons are revolving here. So whenever we are forming solids, in order to form solid, we require a lot of atoms. So during this process, the electrons which are present in the valence shell interact with each other and form something known as valence band. Okay, this is all nice, but what does this term band even means? So band means range of energy level. We can say whatever the electrons which are present in the valence band are of same energy. So the electrons which are present in the valence band are very tightly packed and they can't move freely. So let's see the definition. The valence band is the highest energy band. Why are we saying this is the highest energy band? Because we are talking about the electrons which are present in the outermost shell. So whenever the electron is far away from the nucleus, it has highest energy levels. So we are dealing with the electrons which are present in the valence shell. So this is why we are saying it is the highest energy band in a solid that is fully or partially filled with electrons. So this valence band, now conduction band. So in order to conduct electricity, we need something known as free electrons, right? But we are not getting free electrons in valence band. So we need some other band where we can conduct electricity, where the electrons can move freely. So that band is nothing but conduction band. And this conduction band is right above the valence band. Let's see the definition. The conduction band is the energy band above the valence band where electrons are free to move, allowing electrical conduction in a material. Now let's see what is band gap. So this is all fine. We are learning about conduction band, valence band. This is all fine, but why are we even learning it? Because because of this valence band and conduction band, we define a term known as band gap, and this band gap is essential to determine whether a material behaves as conductor, semiconductor, or insulator. Now let's see what does this band gap mean. So here we have conduction band. Here we are having valence band, right? So the electrons which are present in the valence band, they want to conduct. They obviously want to move to the higher energy state. So the electron which is present in the valence band gains some energy and moves to the conduction band. So the amount of energy required by the valence band electron in order to move to the conduction band is known as band gap. Band gap is not a distance, it is rather an energy quantity. So we already learned that band means a range of energy, right? So valence band have same energy. So electrons which are present in the valence band have same energy. And the same goes with conduction band as well. So we can say that the energy difference between valence band and conduction band is known as band gap. The band gap is denoted by the letter Eg. So the definition says the band gap is the energy difference between the valence band and the conduction band in a solid, determining whether a material behaves as conductor, semiconductor, or insulator. So we all know that the energy unit is joule in SI system. But in this chapter, we'll be dealing everything in electron volt. 1 electron volt is equal to 1.6 into 10 power minus 19 joules. Now let's see what is semiconductor means. Now that we have all learned about band gap, conduction band, valence band, before we go into definition as usual, we'll see what does this even mean. So if you take in the case of metals, we say that metals are good conductors. But why do we say that? Because the valence band and the conduction band in a material are close to each other. If some electron wants to conduct electricity, it can easily access conduction band without need of energy. So it has easy is equal to almost zero. So that's why we say metals are good conductors. But if you take in the case of insulators, we say they are very bad conductors because the conduction band and valence band are far from each other. The band gap is very high for this. That's why we say insulators are bad conductors. But if you talk about semiconductors, the band gap is not that big as insulators and not that small as metals as well. So from this we can say that at times it can behave as metal. So this is for reference. You can see the band gaps of different materials. If you see semiconductors, all of these are quite less. The band gap is quite less. But if you see in case of insulators, it's quite high. So that's what this is. The semiconductor have small band gaps allowing control conduction. Fermi level is a level where the probability of finding an electron is 50%. The definition says the Fermi level is the energy level at which the probability of finding an electron is 50% at absolute zero. So let's see the example first before we completely understand the definition. So it says that the probability of finding an electron is 50%, right? Let's take the case of metal. It is exactly in between the overlap of conduction band and valence band. So it means the probability of finding an electron is equal in metal in valence band and conduction band. If you take in case of insulator, there is a lot of band gap here. So the Fermi level, that means the probability of finding an electron is 50% somewhere in between the band gap. But if you take in the case of semiconductor, it is also in between the band gap, but it is exactly in the middle for pure intrinsic silicon. So this is what it states. In metals, the Fermi level lies within the overlapping bands, allowing free conduction. In semiconductors, it lies within the band gap and shifts based on the doping. In insulators, it is deep inside the band gap, making conduction difficult. So we will talk about this doping and the Fermi level shift in the upcoming video. And I forgot to mention one more thing. The common examples of the common examples of semiconductors are silicon and germanium. So for the pure silicon at absolute zero temperature, the Fermi level lies exactly in the middle of band gap, equidistance from valence and conduction band. So yeah, here it is exactly in between the conduction band and valence band. That's it for today.